Hello, my name is Laurent. I work as a researcher at Jane Street in the London office. Today I'm going to talk to you about our experience using OCaml and Python together at Jane Street, hopefully getting the best out of each language. You probably already know it, but Jane Street is an OCaml shop. We are using OCaml for mostly everything, and there are lots of things that we enjoy about it. For example, we rely a lot on the OCaml type system to guarantee some invariance. It's pretty amazing to be able to refactor some critical systems and rely on the compiler to stop you at all the places in the code that you have to fix. The OCaml performance is also pretty good when using native binaries. And even better than that, the performance profiles are reasonably easy to understand. Python is at the other end of the spectrum. The default version is interpreted, and it's an order of magnitude slower than OCaml. There is also no type checking, and it's quite difficult to reason about large libraries in Python and guarantee that they will behave correctly. So why would we use Python? There are actually quite a few advantages to it. Python has become over the last few years the de facto standard for data analysis. Its lightweight syntax makes it very easy to use, and it has a thriving ecosystem of libraries for numerical computations, plotting, machine learning, etc. A common way to perform data analysis in Python is to use some notebooks. The experience there is very interactive. You just try to adjust the code by looking at the current output until it produces what you would expect. When it comes to, for example, reading a CSV file, extracting a time series of data, and quickly plot the data, and then compute some statistical indicator on it, it's very hard to do better than this notebook experience. Overall, it's quite different from when using OCaml. Python is mostly used as some glue code between different libraries. And in your case, it's mostly to write code that will be discarded soon after being used. Doing so in OCaml would be quite annoying because you would have to handle all the edge cases until the compiler gets to generate the binary. In Python, you can get away by focusing only on the bits that you care about. Though obviously it's easier to shoot yourself in the foot in this setting. So our goal is to leverage Python for this fast interactive development experience, but back this with OCaml services and libraries that are robust and will scale well and perform quite faster. So the standard Python interpreter is called CPython. It actually has a pretty nice C API that can be wrapped in OCaml. For this, we've relied on PyML, which is an open source library. We've built several libraries on top of it to optimize for our main use case, which is calling OCaml code from Python. This actually works in the following way. We compile the OCaml code at the shared library, and then Python loads this shared library and calls the endpoint that will start the OCaml runtime. The OCaml code then starts executing, and it registers various modules and functions using this Python C API. Once this is done, the control goes back to Python, and the Python code can just use this function without even knowing that they actually rely on OCaml code. An important point when devising this Python OCaml interaction is that we wanted to be able to write most of the code in OCaml. Because we have more experience with this language, and also because we have overall better practices. Like we have proper unit testing, continuous integration testing, continuous deployment, etc. And using OCaml for all our bindings makes this interact pretty well with our existing systems, and also in general is good for favoring robustness of the code. That said, we obviously have also put some significant effort in making the exposed function Python idiomatic. For example, we automatically generate some documentation. We try to integrate well with existing Python libraries such as NumPy or Pandas that are very commonly used. The main library that we use to write these bindings is called PythonLib. It extends PyML and provides some easy way to define Python functions from OCaml. You can see an example on this slide doing so. First, at the top of the slide, you have the Python side of the things, where we import a module that is called OCaml, that has been defined on the OCaml side, and we call the approxpy function on this module with an integer argument. You can see then the OCaml code that has been used to generate these bindings. Via PythonLib, we expose an applicative functor that makes it easy to define the argument used by the function. In this case, we have a single positional argument called n of integer type. This applicative functor would also support keyword arguments, arguments with default values, and will help checking exhaustiveness, that all the necessary arguments are passed, and also that no extra arguments are passed, and will return nice error messages if there are any mistakes. We then compute some value on the OCaml side based on this n argument, and finally you can see a Python of float call which converts the resulting OCaml floats into a Python value. Then at the bottom you have some top-level code that creates the OCaml module, and then attach the approxpy function to it. One tricky bit is converting back and forth between Python and OCaml values. In this example, we've only seen very straightforward values to convert, but it's more finicky to do when converting complex values. For example, OCaml records will naturally map to Python dictionaries using string as keys, but doing such a conversion manually would be quite cumbersome. So instead, we wrote a ppx extension to help automating this process. So this ppx extension can be used to annotate any type, and it will generate two functions. Of Python, that is used to take as input a Python object and convert it to the target type, and to Python, that goes the other way around, converting the target type to a Python object. All the basic type will be automatically mapped to the equivalent type on the other side, and we also have an annotation at python.default so that some fields can be optional and get some default value. This is quite useful because it avoids Python user needing to populate all the expected fields. One tricky bit is the encoding of OCaml variants, as there is no clear equivalent on the Python side. Currently, what the ppx will do is use a pair, where the first element of the pair is the constructor name, taken as a string, and the second argument of the pair will be the arguments of the constructor. We tend not to use it a lot, so most of the time we just avoid exposing types that involve variant and try to rely more on records. So we mentioned that we've used PythonLib to expose a wide variety of libraries and services in Python. Actually, we've exposed a bit more than 35 of them at this point, and one of these libraries is quite special. It's the Toploop API. So this library that is provided by the OCaml compiler lets you build easily some read eval print loop environment. By wrapping it in Python, you can pass it a Python string that contains some OCaml code, and then evaluate it. So we've put together such bindings, And we also used some Jupyter magic. So on the right-hand side of the slide, you see some Jupyter cells. And for example, this %% OCaml magic, what it will do is take the content of the cell as a string and pass it to some Python function. This Python function will then pass it to the OCaml side and to the top loop library there, so that it actually gets executed on the OCaml side. So you can just have cells that contain OCaml code. You can see on the next cell another magic that is % OCaml. On the line RPN equals % OCaml RPN, the % OCaml will convert the OCaml values to Python values, and it even works for Clojure. So the right-hand side RPN is actually the OCaml function, and the left-hand side is the resulting Python function. And then you can see over the next two lines that this Python function can be used as any other Python function. So we mentioned at the beginning of this talk that we enjoy the performance of OCaml. Now that we have this integration of the OCaml top loop in the notebook, it's quite easy to check that. So here you can see in the top cell an implementation of the n-queens algorithm in OCaml. This algorithm just counts the number of ways to put n-queens on a n by n checkerboard. It's a pretty backtracking approach, and it serves us as a CPU-intensive benchmark. So we define the function in the first cell, and in the second cell, we make a Python function out of it, and we compute the output on some values. Then we of course do the same on the Python side, writing a function to compute the equivalent output, but using Python code, and we try to stick to the same algorithm. You can see here a comparison of performance. The left column is the OCaml timing, and the right column is the Python timing. And OCaml turns out to be a bit more than 5 times faster than the equivalent Python algorithm. It's actually even better than that, because we use here the bytecode version of OCaml. Switching to native code would likely make the difference even larger. So writing such bindings has proven to be quite an easy thing once we had the proper idioms in place in PythonLib and once we had this PPX extension. But not everything is actually easy. So a pretty tricky part is managing memory. We want there the two memory models of Python and OCaml to line up. As most of you probably know, OCaml has some form of garbage collector to manage the memory. Python, on the other hand, uses ref counting. It still has a garbage collector to handle cycles. So when values are exchanged between the two runtimes, we would have to inform the runtimes about what just happened. For example, if you take a Python values and pass it to the OCaml side of things, you will have to increase your reference count. And then when the value disappears on the OCaml side, you can decrease the reference count, and you can use a GC finalizer for that. Conversely, if you pass an OCaml value to the Python side, you want to inform the OCaml garbage collector that it's not safe to compute this value for now. And once the Python side has released the value, you can tell the garbage collector that it's okay to collect it. So that tends to work fairly well in practice. However, there is a tricky part when it comes to cycles that cross the Python OCaml boundaries. Such cycles will be a Python value that has a reference to an OCaml value, and this OCaml value has a reference back to the same Python value. In that case, the Python runtime cannot decide to collect the thing on its own, because the OCaml value, it knows that it has some reference count that is 1, and it's the end of the pointer that it can see. So the Python GC cannot do anything. And it's the same for the OCaml GC. The OCaml GC sees the OCaml side pointing at some Python value. It knows that these Python values are live, but it doesn't know that these Python values are pointing back at OCaml. So none of the two runtimes can decide on its own to garbage collect the thing. We actually don't have a very good solution for that at the moment. We rely mostly on automated tests to monitor for memory consumption and check that such cycles don't appear, and on reports from users. So we already had the case of such a cycle occurring in practice, and hopefully that will not happen too often because it starts to be a bit of a convoluted setting when you have pointers that cross the boundaries both ways. But still it's something that can happen. So there are multiple things that we would like to work on next to make these bindings even better. The first thing is improving the cooperation between the OCaml and the Python runtimes. So we use async on the OCaml side for async computations, and currently when the OCaml code is running, the Python code is blocked. And when the Python code is running, the OCaml code is blocked. This makes it quite easy to reason about the code, but is far from being optimal. And we would like to improve that by letting both the OCaml and Python side run simultaneously in different threads. Ideally, we would even be able to map the deferred values from OCaml async to the equivalent Python values, which is the async await syntax. That would be fairly neat because this way a Python user could decide in its notebook to trigger an OCaml computation. He would immediately get the control back, be able to work on other stuff, and at some point to check back the results of the computation, or to tunnel the computation to another function and get a deferred for the next stage of these computations. We would also like to improve the user experience. So for example, our users tend to rely a lot on pandas data frames, and using a library like Arrow would make it nicer to exchange data between the two different sides in this format. It would even be possible not to have to copy the data around each time. We would also like to make the bindings more Python idiomatics and more transparent, like have nothing that lets the Python runtime know that they're actually not real Python functions. Finally, we would like to make it easier for people to write Python bindings. An idea that we already looked at in the past is automatically generate these bindings from the OCaml compilation artifacts. So what we did is, using the CMI compilation artifacts, automatically generate some OCaml code that will wrap the code that produces the CMI in a way that can be used in Python. The prototype that we had worked well, but it has the drawbacks that the generated code doesn't look very Python idiomatic most of the way. So there are probably two ways to improve on that. One of them will be to accept that the code that you generate is not very Python idiomatic, and then have a Python layer that would, on top of it, do the conversion to make it nicer on the Python side. The benefit of this approach would be that it will be easier for users to hack around, and if they don't like the conversion glue that we added on top of the OCaml function, they would just be able to copy and paste the code and tweak it. Another way to get around that would be to annotate OCaml functions with some form of PPX, so as to decide that they're exposed to the Python runtime and give some hints about how the parameters should be handled. That's what something like the BIOS crate does in the Rust world. So yeah, you can find all our code on our GitHub repository. You would want to search for pythonlib and ppx python. And that's pretty much all that I wanted to talk about today. So please, if you look at your code and have any feedback or questions about it, just reach out. Thank you for your time.